Hello everybody, welcome back to the NCL Railway Cyber Twin training video. So here is a quick overview of what we will be covering in this video. Today, we'll be diving deeper into how the railway system works and how the components communicate with each other. We'll assume you have a basic understanding of computer networking, how OT protocols like Modbus and S7COM function, how PLCs and RTUs work, and what ladder logic is. By the end of this video, you will be able to explain and trace out how the trains, HMIs, and signaling system communicate with each other via OT protocols. You should also be able to reason out how external modifications made to the railway system's inputs and communication protocols may impact the trains and signaling systems on the physical real-world simulator. So, let's start off with the three main parts of track signaling: track station, track block, and track junction signaling. This will help us to understand the role of PLCs in the track signaling logic and how the HMIs influence the signaling outputs. We'll then move on to how the train's information is sent to the RTU and HMI, and what aspect of theirs are being controlled by the PLCs. Lastly, we'll provide any additional information that may help you further understand the workings of the system. Great, let's dive deeper into understanding how the railway system works. For track signaling, from the physical real-world simulator, the train position sensors, which are the small grey boxes placed at fixed intervals along each track, send their states to the input registers of their respective track signaling PLCs. These PLCs can be the station, junction, or track block PLCs. The PLCs take the values in their input registers and execute their ladder logic to update their coil states. The output of these coil states then determine which signals are turned off or on, green or red. The HMI corresponding to the PLCs also communicate with the PLCs through Modbus TCP. These are either register read, register set, coil read, or coil set requests. The read requests help the HMIs collect information about the track, and the set requests allow the HMIs to interact with and influence the track. Now, for the PLCs that control the train stations, there are three PLCs used, where PLC 03 is the master, and PLC 04 and PLC 05 are the slaves. These PLCs control if and how long the trains dock at the station and their departure. There are a total of 22 input sensor states into the PLCs, with 22 total ladder logic to calculate and output to 22 signals. Each station is controlled by one train position sensor in the middle of the station and one train block signal that corresponds to both the entrance and exit signals of the station. You can refer to the logic circuit on the right to understand how the ladder logic has been designed. In this short clip, we can see the train CC Line 1 passing by the station Kentry. This is on the physical real-world simulator. As the train passes over the middle of the station, the sensor on the station is triggered, and red signals appear in front and behind the train. The front detection sensor of the train sees these red signals and causes the train to come to a stop. On the railway signaling monitor SCADA HMI, we can see that the station Kentry changes colors. It was previously a grey box surrounded by a green box, and is now a yellow box surrounded by a red box. The inner box changes colors from grey to yellow because this is the train position sensor at the station, indicating that there is a train that is currently on the sensor. The outer box changes colors from green to red because these are the front and back exits of the station signals being locked. This indicates there is still a train being docked at the station. You can also see these signals change on the PLC monitor as well. For input register CCST04 and output coil STCC04, which is Kendry station. Now, once the train has finished at the station, the red signals at the front end and the back exit of the station turn off. The train is then able to move off. And the station reverts to normal on both the railway signaling monitor SCADA HMI and the physical real world simulator. This network diagram helps to summarize what we've just gone through for track station signaling. Now, let's move on to track block signaling. There are two PLCs used to control the track blocks, where PLC 8 is the master and PLC 9 is a slave. They take in a total of 29 input sensor states, which are passed through 15 ladder logics in the PLCs and output to 15 signals. Now, the railway's track block signaling is a simplified version of fixed block signaling. Firstly, each track is divided into segments, or track blocks, with signals positioned at the entrance of each block. At each fixed distance on the track, there is a train position sensor, a small grey box, that detects when a train enters or exits the track block and sends its state to the PLC. The PLC processes the data and in its input registers with its program ladder logic, then updates its output coils. The state of the output coils are communicated to the respective signals through physical connections. If there is a train in the track block, the output coil is high and the signal is set to red. If the track block is empty, the output coil is low and the signal is set to green. To prevent collisions, trains can only enter a block whenever the entrance signal is green, thus ensuring only one train occupies each block at a time. So, in this clip, we have the train CC Line 2 traveling along the circle line. On the physical real-world simulator, you can ignore the signal 1 on the right for now, as we will not be focusing on it. Now, as the train passes over the middle sensor S15, notice that the signal behind it, signal 8, turns from green to red. This indicates to any train behind that there is a train in the fixed block. Now, as the train passes over the next sensor 2, the signal 8 turns back to green. It's passing over sensor 2 now, and signal 8 will turn back to green. Now this indicates that the train, CC Line 2, has passed through that fixed block and into the next block. Now that we know what it looks like in the physical real-world simulator example, let's look at track block signaling in general. We have the signal N, the sensor N, and the sensor N plus 1. When a train is passing by sensor N, its state is sent to the track block control PLC's holding register 1. Sensor N plus 1 state is also sent to holding register 2. Remember that the railway track block HMI has an override checkbox for each track block that can disable any changes to the track block signal. This state is sent to holding register 3. The PLC then executes its ladder logic and outputs to coil 0, which updates the signal N. The PLC only executes its ladder logic when either of the sensor states have been updated. This network diagram helps us to summarize what we've gone through for track block signaling. Okay, we now move on to how the track junction signaling works. There are three PLCs used to control the track junctions, where PLC 0 is the master and PLC 1 and 2 are the slaves. They take in a total of 39 input sensor states, which are passed through 17 ladder logics in the PLCs and output to 19 signals. Each junction is controlled by 2 or 3 ladder logics. For each ladder logic, 2 or more sensor states are read to control 1 or 2 signal states, depending on the junction's complexity. On the right side, we can see one such junction which uses the logic of a T flip-flop in its ladder logic. We will not dive deeper into how each and every function works, each junction works, as a general understanding of the junction should allow you to be able to interact with them and adapt to the junction's unique situation. Now, for this video, we have two trains, CC line 0 and NS line 0, traveling along intersecting lines. Both trains are positioned right at the start of the junction. On the physical real-world simulator, notice that NS line 0 reaches its NS line sensor 2 first. Therefore, the circle line's signal 2 turns from green to red first. Although they are different lines, the north-south line sensors affected the circle line's signals. This junction logic prevents trains from separate lines from crashing into each other at the junction, as opposed to a normal track block's logic to control only its own line. After the train NS line 0 has crossed the junction, it triggers the NS line sensor 3. The circle line's signal 2 turns from red to green. This allows the train CC line 0 to finally move into the junction, which triggers the circle line's sensor 4, and so on. On the signaling monitor SCADA HMI, we can see the sensors being triggered. The PLC inputs and outputs, and lastly, the affected sensors changing. This network diagram helps us to summarize what we've gone through on track junction signaling. Great, now that we're done with track signaling, let's move on to train control. There is one set of PLCs and one set of RTUs that help us manage the trains. The PLCs 6 and 7 manage each train's third rail track switches, which is essentially the power for the trains. The train's internal circuit state, which draws power from the third rail track, is either on or off, and is input into the PLC. There is one for each train, so 10 trains means 10 input registers total. These PLCs have 11 output coils. Each train's third rail track switch takes one coil, where on means that the third rail track switch is closed and the train is receiving power. The last coil is for controlling the train's collision avoidance system, which affects all of the trains. If this coil is on, the trains can see if there are any trains ahead of them and automatically stop themselves before they get too close to crash. Now, for RTUs 0 to 9, they monitor the train's information and relay it to the train controller HMI. The west-east lines trains 0 to 3 correspond to RTU 0 to 3. The north-south lines trains 0 to 2 correspond to RTU 4 to 6. And the circle lines trains for 0 to 2 correspond to RTU 7 to 9. Each train provides its front detection sensor state, current, voltage, and speed to the RTUs. 4 for each train means there are 40 inputs in total to the RTUs. Let's break down and analyze the different components of the train. Assuming the train is traveling facing the right, in front of the train there is an invisible detection area. This detection area checks if there are any signals or trains in front of the current train and updates the front detection sensor state accordingly. This front detection sensor state is passed together with the speed, voltage, and current to the RTUs by physical connections. The RTU collects the inputs from each train and sends it by S7COM to the Railway Trains Controller (HMI). From the HMI, register read requests or coil set requests can be sent by Modbus TCP to the train control PLCs. Each train's internal circuit state, whether the train is being powered and functioning, is sent to its corresponding holding register. If this is the West-East Line Train 0, then the state is put into holding register 0. The West-East Line Train 0 also has its corresponding coil, coil 00. This coil 0 then controls the West-East Line Train 0's third rail track power switch, which controls whether the train receives power. The West-East Line Train 1 corresponds to holding register 1 and coil 01, and so on. The train's controller HMI can also control coil 10 on the train control PLC. This coil 10 determines the auto collision system on the trains and will prevent trains from crashing if it is high or enabled. This is a network diagram to help us summarize what we've gone through on train control. Okay, let's review the network diagram again. You should now know which HMIs, PLCs, or RTUs communicate with each other and how they communicate, either through S7COM or Modbus. You should also understand how each PLC controls the railway system and predict the possible ramifications of changing the value of an input register or output coil on the PLC. Here is some additional information that can boost your understanding of the OT protocols, or to find out more about their vulnerabilities in the railway system. The PLC and RTU simulation program are as follows. To differentiate between Modbus and S7COM, you can filter them using their respective TCP port numbers. Note that S7COM uses a different packaging from Modbus, so any packet modification should adapt to that packaging. Only the HMIs are whitelisted to send packets and communicate with PLCs on Modbus TCP and S7COM. Any other packets with the PLCs as the destination will be ignored. This whitelist is on the VMs controlling the PLCs and not the firewall. So the packet is ignored after reaching its destination PLC and is not dropped. Alright, that's the end of this training video. I hope you now understand how the trains, HMIs, and signaling systems communicate with each other via OT protocols. You should also know how the signaling systems and train controls are controlled. You should also be able to reason out how external modifications made to the railway system's inputs and OT protocols would impact the trains and signaling system on the physical real world simulator. Thank you.